Hello everyone, welcome to another Physics 30 example. This is Unit 5, which is Atomic Theory, and this is Lesson 4, where we start to look at the Compton effect. So here's our example. We want to know how fast an alpha particle would have to go to have the same momentum as a photon with 7.3 mega electron volts of energy. So let's think about this in two ways. Let's first of all write down what we know about the alpha particle. Okay, so the alpha particle has a mass, which means we can talk about the alpha particle and its momentum as being mv. Okay, it's a regular particle, it's an object, and so we can talk about it like this. So let's call this alpha, alpha, alpha. So P alpha equals M alpha V alpha. Okay, we also have a photon. Now, we should remember that when we're talking about photons, we can't really talk about a photon. I'm going to write it like this. Photon momentum is mass of the photon times the velocity, while the velocity is going to be c, because it's the speed of light. Trouble is, photons have zero mass. So does that mean they have zero momentum? And this is where we get into our nice little derived equation using, we're using E is equal to mc squared, which we know from Einstein. And then we also know, well, P is equal to mv from Newtonian mechanics. So if we were to rearrange this for m, we would get E over c squared. And that means we can then plug this in to our momentum equation. We can substitute this in. So we can say that P is, rather than m, we're going to say that it's E over c squared. And then, of course, because we're talking about light, that's going to be c. And that gets rid of the mass. That means we don't have to think about mass. We can talk about mass, as we've covered in class. We can talk about mass as an energy over c squared unit. It's an energy equivalence. That's really what Einstein taught us with this equation. So this obviously cancels out, and we end up with momentum being equal to energy over the speed of light. Actually, if you want to go slightly beyond Physics 30, we can talk about Einstein's real equation, which is this one here. You can see it's a little bit more complicated than what we normally talk about. And that's because it's relativistic. So if something has no mass, if you were to get rid of this mass, if the mass was zero, then you can see you end up with E is equal to PC, which is effectively what we just did here. And that's to do because this equation, the one that we're so familiar with, is only valid when there's no speed. It's a rest mass. So if there's no speed, there'll be no momentum, and so we can cancel these out. This PC would be zero, which means you're left with mc squared. So you either talk about zero mass, or you talk about zero speed, and you can simplify this equation, and that's kind of where this comes from. Anyway, we don't need to know about that for Physics 30, just as an interesting aside. Anyway, back to our statements over here. We've got two things to talk about now. So there's my momentum of the photon right here. This is going to be the momentum of the alpha particle. So we're going to put them together. So we're going to start off by saying that, let's use red here. I'm going to say that just to restate the question in another way, I'm going to say the momentum of the alpha particle has to be equal to the momentum of the, I'm going to do that again, of the gamma, the photon. Okay, so those two things have to be equal. And so now I can substitute in what I have. So I've got the alpha mass, the alpha velocity, and then I'm going to go energy of the, energy of the photon divided by the speed of light. So now I've got everything I need. I know the mass of an alpha particle, it's a known value. I know the energy of the photon, that's given in the question, and of course I know the speed of light. So I can now rearrange this and solve for the speed of the alpha particle. So the speed of the alpha particle is going to be, I'm going to go, 7.3. mega, so that's times 10 to the 6 EVs, divided by speed of light, which is 3.0 times 10 to the 8, that's meters per second, and then the mass of the alpha particle, which is 6.65 times 10 to the negative 27 kilograms, and that's going to give me the speed of the alpha particle, which is, if you put that in, 5.85 times 10 to the 5 meters per second. Okay, so example number 2, we have a bit more of a classic Compton situation. We have an X-ray, so we've represented it as a photon, like a little particle, and that's coming into a free electron. So this electron is, we're assuming it's not bound by anything. There's no energy, it's not moving, so we can go ahead and use conservation of energy. And then this photon is going to collide with it and bounce off in this direction in an elastic collision. So we can use conservation of momentum as well. And we know the angles. We would have measured this photon here, and that means we can make some predictions about where the electron would go with regards to the angles. Compton would have used conservation of momentum, conservation of energy to derive his formula, which we are familiar with, and here it is. What's important here is the angle. So really, really important to note that the angle that we use is this one here, okay, the whole thing. So of course, there's a 90 degree in here, so the theta that we're going to need in our calculation is going to be 17 plus the 90 plus the 21.6. So we need to make sure we keep track of that, and that's what we need to use. The other thing to pay attention to is the theta that you get from the Compton equation. It's actually the change in wavelength. So watch out for that on diploma questions. You'll come across one of the distractors is guaranteed to be just the change in wavelength. That's what you're going to get out of your calculation, but then you have to think about the initial and the final. So it's worth mentioning that delta lambda is actually going to be equal to the, let's do that again. It's actually going to be equal to the final wavelength minus the initial. And that's important because the photon coming in, this wavelength here, this initial wavelength, is going to be smaller than the deflected wavelength. Because if you remember the larger wavelength, so larger wavelength equals smaller energy, right? And it's going to lose energy as it goes through its collision. So let's plug in what we know, and this should be pretty straightforward. We are going to get our delta lambda. So we're going to put in all our values, and we get to here. Notice that I'm using Planck's constant in joule seconds. For the mass, I'm using the mass of the electron here that's involved in the collision, obviously the speed of light, and then I've combined all of these angles in here. That's going to give me a delta wavelength of 3.135 times 10 to the negative 12 meters, and remember that is equal to lambda final minus lambda initial. So to get the final, which is what I'm trying to find here, I have to add that initial. So I'm going to go ahead and go, let me do that again. I'm having problems here with my lambdas. The final is going to be 3.135 times 10 to the negative 12 plus this here 2.8, and it's pico, which is negative 12 times 10 to the negative 12. And so that's going to give us 5.935 times 10 to the negative 12 meters. In other words, it's going to be 5.94 to 3 significant digits, and I'm going to call that picometers. Okay. Part B of the situation, I'm determining the kinetic energy of the electron. So of course, I'm going to do a sum energy equation. So the initial energy, the total initial energy, has to be equal to the final energy. And what's the initial energy? Well, that's going to be the energy of this photon here. I'm going to call this the energy of the photon initial. So that's going to be here, energy of the photon initial. And that's the only thing coming in. Of course, what's coming out is the energy of the photon final and the energy of the, well, this would be the kinetic energy of the electron. So I've got the energy of the photon initial coming in, then I've got the energy of the photon final coming out, plus the kinetic energy of the electron. So what's the kinetic energy of the electron? Well, it's going to be the initial energy of the photon minus the final energy of the photon, and that's going to be our kinetic energy. Okay, so what's photon energy? Well, it's going to be hc upon lambda, and this is going to be my initial, minus hc upon lambda final. This is the wavelength that I just calculated in the previous example, and that's going to be equal to my Ek of my electron. So let's plug that in and see what happens. And so there we have it. We got our Planck's constant in joule seconds. That's important because we're going to talk about kinetic energy, which we really like to use joules for. Not essential. You can talk about kinetic energy in electron volts, but if you do, that means you can't then get the speed. So it's more common to talk about kinetic energy in joules. And we're going to use the speed of light. This is the wavelength of the initial photon. This is the wavelength of the final photon. And there's our answer, 3.75 times 10 to the negative 14 joules. So part C of our example gets us to sketch a vector sum diagram. This is a tail to tip vector diagram to illustrate the conservation of momentum. So let's just color code the bits that we want to. This is going to be this here, this red line. This is the total momentum before, so initial. And then I'm going to use green here to show the total momentum afterwards. Well, it's going to be split into two. So we've got this is the momentum final, and I'm going to call that 1. And then this is also part of the total momentum, the momentum final 2. So I've got to write a statement to say that the momentum total initial must equal, actually I should have used red feather, it doesn't matter, is equal to the momentum final 1 plus momentum final 2. And I just have to use vector diagrams to show that. So let's go back to my red. I'm going to start off when we do our vector sum diagrams. I'm going to put the total momentum initial in. So there it is. Let's call that the momentum total initial. And then all I have to do here is use the 2 green arrows, and I have to start from here and end here so that they give a 0 sum net. So I'm going to go, let's do momentum 1 first of all. This is not to scale, so I'm going to go to here. That's my first one. Let's label that momentum final 1. And then my momentum final 2 is the electron, and that's going to go all the way, again, not to scale. It's going to go to here. And so that's my momentum final 2. That's my vector diagram. So in this third example, we're going to demonstrate that we can actually go ahead and just use straightforward Unit 1 conservation of momentum principles to analyze a Compton collision as well. So I'm going to use red to represent everything in the X, And let's use green to represent everything in, oh, not that one, this one. I'm going to use green to represent the y. So first up, let's just go and sketch them in. Let's just recognize that that there is a y component, that there is a y component, nothing on the other one. And then in red, we've got this, and we've got this here. So I'm going to call this x final 1. This is x final 2. This is x initial, and that's actually the total momentum. And then let's call this y final 1, and this is y final 2. So let's look at our x momentum. We're going to start off by saying the total x is going to be, or the initial is going to be equal to the final. Okay, and so hopefully you can see we've got a value coming in. We're going to say that 50, and this is Otto's, which is times 10 to the negative 18 kilogram meters per second, is going to be equal to x, I'm just going to go 1, because I know it's in the x direction, plus x2. Okay, now what are those? Well, let's put those in. x1 is going to be what we're looking for, so I'm going to leave that as x1, but I have to add x2. Now x2 is going to be in the negative direction, so I need to make sure I keep track of that, and it's going to be the opposite side of this triangle here. So this x2 is going to be 40 times 10 to the negative 18. I'm not going to put the units in for now. And it's opposite, so sine 30. Okay, so I'm going to put that in. 40 times 10 to the negative 18 sine 30. Okay, and of course what I can do then is solve for x1, because this is 50 times 10 to the negative 18. So x1 is going to be, let's write it out, 50 times 10 to the negative 18 minus, this ends up being 2 times 10 to the negative 17. So that means that my x1 final is going to be 70 times 10 to the negative 18 kilogram meters per second. Now what of course I'm doing here is I'm building a triangle that's going to represent this over here. So I've just figured out x1, which is this final x1 over here. So let's go ahead and just draw that in. I'm going to draw that over here. I'll use red. There's my x1, and I know the value. It's 70 times 10 to the negative 18. I'm not going to put the units in for now. Now I need to find y1. So let's go ahead and do that. Okay, well, it's the same principle. I'm going to say the momentum in the y initial is equal to the momentum in the y final. The initial actually is 0 because there's no vertical initial momentum. And then I can just go ahead and say that it's going to be the momentum in the y1 plus the momentum in the y2. In other words, these two are equal and opposite. So if I work out this one, it's going to be that one. If to restate it, that would be that Py1 is equal to Py2. So what is Py2? Well, if we find that out, we get our answer. So Py2 is going to be the cosine, or the adjacent, it's the adjacent angle of this triangle. So it's going to be 40 times 10 to the negative 18 cosine 30. Okay, which is equal to 34.6, keep some digits in there, times 10 to the negative 18. So that can come into my triangle, which is here. That's going to be 34.6 times 10 to the negative 18. And now all I have to do is figure out the resultant, which is going to be this one. And of course I need the angle. So that's going to be, this would be the opposite, this would be the adjacent. So I'm going to say that tan theta is 34.6 over 70. And that gives me a theta, if I plug that in, of 26.3 degrees. And I'm probably just going to go to 2 significant digits because that's what I have here. So just 26 degrees. Let's get rid of the decimal 3. There we go. 26 degrees is my angle.